So we're continuing with this worksheet, and we've arrived at an isobaric expansion down here. Sorry, right there. If you're looking above, we've considered separately a constant volume heating process, and I'm pointing out that the same approach there to problem solving would apply in a constant volume cooling, for which there's no specific video explanation. And similarly, there is a video on the constant pressure heating problem, and the same approach to problem solving would be considered for a constant pressure cooling problem, for which again there's no specific video because it is so similar, except for the direction of heat flow and the impact on the signs of those changes. We've also noted separately that the words cooling and adiabatic to describe a single change are not compatible, and therefore this is not possible excuse me, because simply adiabatic dictates that there is no Q exchanged between system and surrounding, whereas cooling would imply that the system loses heat to its surroundings. So we've not considered that at all. We've arrived therefore at a constant pressure expansion question, or change, and so let's consider that, an isobaric expansion. Isobaric pressure is constant, and therefore delta P is equal to 0. And it is an expansion. Okay, so delta V is greater than 0. And all of these are for a perfect gas. So initially I have N1, T1, P1, V1. It's undergoing this change. It's a closed system, N2 equals N1. Just going to write T2 here, and P2 and V2. It is an expansion, so I can say right away that V2 is bigger than V1. It is isobaric, so P2 is equal to P1. And now I'm wondering about the temperature. I wanted to expand, so say I have my plunger here. The gas is in here, and I want it in state 2. I didn't write state 1 and state 2 at the top, but that's implied there. So I wanted to expand, and I want to think about this physically, logically, what needs to be in place. Okay, the gas has a bigger volume. There's my expansion, a bigger volume. I want the pressure of the gas to be the same. So if P1 is the initial pressure of the gas, and P2 is the final pressure of the gas, and I want an expansion, so I want the pressure to stay the same but the volume to get larger. What has to happen to that temperature? If that temperature didn't change, then it couldn't possibly exert the same pressure when it occupies a larger volume, because I have the same number of moles. So if I want the pressure to stay constant, but I want the volume to grow, I have to have the temperature higher in the second case, so it must be greater. So T2 is greater than T1, but we've arrived at that conclusion here by thinking about the question. It wasn't explicit in the description. Okay, so because T2 is greater than 1, or sorry, greater than T1, then delta T is greater than 0, and delta P here is equal to 0, as we said, and delta V is greater than 0. Now, because the temperature is going to increase, then that means, what have we done in terms of Q? What had to happen? If the temperature has increased, but it didn't increase because I was compressing it, it's expanding and heating. It's not going to do that spontaneously. It's because I've added heat to it. And so it must be the case, therefore, that Q is greater than 0. It must have been heated, so it must be heated during this change. In order for the temperature to increase, in order for the pressure to stay constant, even under the condition of expansion. Okay, so the system must be heated. That's great. The volume changed, and so what does that tell you about any work that was or was not done? Work is less than 0 because the system did work. So energy has left the system as work. When the system does an expansion amount of work, then energy is leaving the system as work. You can imagine it pushing that up, and so energy is leaving the system as the work of expansion, and therefore, in a system's perspective, W is negative, if you like, less than 0. Okay, so I have all of that. Now I want to do formulas. And so there's my whole physical change that's going on. And now I want to consider the first law. So delta U equal to Q plus W, and du equal to du plus dw. It's constant pressure, so dq, remember we have heat, it affects a temperature change, depends on the heat capacity of the substance. Rearranging, I have dq is c dt, which really is incomplete, and in terms of this change, I have dq constant pressure, so sub p, and that is equal to ncp, so cp, because it's constant pressure. This is a molar quantity, so it depends not only on the heat capacity of the substance, but how much is there. And then I have dt, so this is good, that's ready to integrate. However, a dq sub p, the heat exchange between system and surroundings under a constant pressure condition, is also equal to the enthalpy change. So I get to do two things here because of this equality. And so now I integrate everything, and so when I'm calculating Q sub P, the heat, I'm actually at the same time computing a delta H in this case, and that is equal to an NCP delta T. So I integrated the whole thing above over the temperature change. That's great. Now if I'm asked to find the work associated with this, dW always start with a minus P dV, and we did this in another video too, but it's worth repeating. So we said that this was reversible. The irreversible changes are coming up, but we said that this was reversible, and so it's reversible but also constant pressure. And so I'm wondering here what to do. So let's do what we've done this before in another video just to demonstrate. Because it was reversible, we might very quickly do something like this. So let's go and integrate it. Instead of writing minus PdV, I'm going to substitute P is equal to nRT over V. And so I'll carry the negative sign, nRT over V, so I'll write it like this, dV. And then in my next step, I would pull out what's constant, so N and R and hopefully T, but it's not because it's heating. And so really this doesn't get me anywhere. It's not that it's not true, it's just that it's not helpful. And so let's try that again and integrate dW and integrate minus PdV and realize that in fact the work here is equal to a minus P delta V because the pressure is constant, but I have a volume and a temperature change. And so what P do I use here? Let's come back over here. So the pressure initially is the same as the pressure finally, and it really is the pressure against which my gas is expanding. So we talk about a P external, that's the pressure down, like this. So the external pressure and the internal pressure, which is the P initial of the gas in this case, are the same because I'm in an equilibrium state 1. And after the change is completed, I also have an external pressure, like here, and a P2, which is the final. They have to be equal because this thing has stopped moving, and I'm in an equilibrium state 2. So in this question, my initial pressure of the gas and the P external initial, and the P final of the gas and the P external final, they're all the same. Because what happened is Q came into the system to start heating it, but it expanded, and so the pressure was able to stay the same the whole time. And so I would have to write it like so, even though it is reversible. Even though it is reversible, I write it like this. Okay, so work is equal to a minus P delta V. Let's see, we had Q, W, delta U, delta H. So if I find my Q, delta U is equal to Q plus W. So when I calculate Q and I calculate W, this is not in focus for some reason, I can just add those together. There's my work and my Q. I can add them together and get delta U. And the following is also true. Delta H, or I should say H, is equal to U plus PV, another starting point. So delta H is equal to delta U plus the delta of the PV. And so delta H is equal to delta U plus, it is P constant, delta V. So I can do that. Remember, we also, we could substitute PV is equal to nRT, and we said that delta H was equal to a delta U plus a change in the nRT, and because N is constant and R is constant and oops, T isn't, this would be delta H is equal to delta U plus N R delta T. So there are a number of formulas that actually work here that we could use. So I could find this right here, and that would be this, and then I could do this and find delta U, or I could find delta U this by adding Q and W together if I do it that way, but they will all be compatible with each other. And so that's the end of this one.